Welcome Mechanics of Materials students. In this third lecture on beams, we're going to be addressing longitudinal stresses, and these are stresses that are normal to a cross-sectional face. Therefore, they are axial stresses or longitudinal stresses in a beam. But we're going to specifically address the ones that are generated as the result of bending the beam. So when we looked in statics at the bending moment, the bending, basically force, moment, internal moment due to external forces as a function of position down the beam, that moment basically is flexing the beam. And in this section, we're going to look at how does that state of flexure affect axial or longitudinal stresses. Axial and longitudinal are synonymous. From that standpoint, we can also have axial or longitudinal stresses due to just literally axial loads, like the beam literally being stretched in the axial direction, and that was represented by our normal force N at any cut section. So this would be in addition to that normal force, but ultimately generated by our big M at any X point on the beam. So we're going to start out by looking at a 2D beam, and so we're going to superimpose a grid on this beam, and we're going to pick out a couple of points. We have points A and B right in the center of the beam. So this is the center line here, right down the center. So that would be that line would be going through a point that is in the centroid of the cross-sectional face. And we're also going to define a couple of points C and D above it that are separated in the y direction by some delta y in this direction. We can see our axes better here. So we're going to take that beam and we're going to flex it. We're going to bend it basically. So we're going to take the ends and pull them up, and the middle goes down. So if we imagine a point on the origin, kind of right here, x-axis is going in this direction, y-axis is vertical. We're going to apply bending moment, and the beam's going to look like a smiley face. So we're gonna look at how things stay the same or change, and think about the state of stress in different directions as a result of this bend. So one thing we can take a look at is we can now define some radius of curvature at this point. We also know we haven't bent this beam into like a circular arc, and because it's not a circular arc, presumably it kind of flattens out as we go on. So this radius of curvature is probably going to be greatest straight down, and then as you get further out, it's going to get bigger and bigger until we've kind of defined a straight line further on. So it's not a constant radius of curvature, and we can draw that radius to any point kind of in the y dimension of the beam, so going down deep into the beam. So we're going to define a value rho as going from the origin from which we're going to draw our radius of curvature down to the line that connected AB. And so we can define another rho to the line that's connecting C prime, D prime as being some rho minus y, because it's closer to this center point. And we've subtended some angular distance delta theta. So let's go back to our unbent beam and notice that the distance between points A and B is delta x. So we've got delta theta being our little arc that over which our radius of curvature rho holds. So it's a small arc, so we're going to approximate that over that arc we got the same radius of curvature, even though the radius of curvature changes with position down the beam. And we're starting with a distance between A and B of delta x. So let's make some assumptions about what's happened during this flexing. So let's look at the normal stress in the z direction. So that's coming out of the paper, right? So we got x going upwards, z going in the direction, or excuse me, x going in the direction that was originally down the beam, like lengthwise. So z is kind of coming out of the page at us. We're saying there's nothing grabbing onto the z. It's a free surface on both sides, and there's nothing that would impart any loads in a z direction, directly or indirectly. So we're going to say sigma zz is 0 everywhere. We're going to say that the bar height in this direction doesn't really change much. That dimension is preserved. So for that dimension to be preserved, that means we're not compressing it, we're not extending it, and that means the strain in the y direction, so epsilon y is pretty small, so that must mean sigma y is also pretty small. So there's not much strain in the y direction. So we're going to assume that that is negligible. We're also going to assume that the grid squares here, stay pretty much square as we bend it. Obviously, they're going to deform a little bit, but not significantly. So if these squares stay pretty much square, then we know the definition of a change from a right angle to an acute angle or an obtuse angle is defined as our shear strain. So if we say, well, all these squares stay square, another way of literally saying that is that the strain, the shear strain in the xy is really small. Which means if the strain in the xy is negligible, even though our shear modulus is pretty big, the shear strain in the xy will also be small. So we're kind of ending up in a similar situation that we did for torsion of a circular shaft, where the geometry of our bend is such that there's not a lot of strain or a lot of stresses that are existing, in any direction. There's a few and they're big, but the others are negligible. So the geometry of flexure in a single dimension allows us to really zero in on the stresses that are going to end up, as we'll see, being pretty darn big. So just to recap, summary of our bending geometry. Planar cross sections perpendicular to the beam axis remain planar and perpendicular to the bent axis. So basically our ZY face stays intact. So we're just kind of tilting it. We're not bending it this way. We're just tilting it out as the whole beam flexes. So no shear there. No stress in the no normal stress in the Z, no normal stress in the Y. Straight lines parallel to the beam axis assume a curved shape. So we went from a straight line connecting A to B to this curved line connecting A to B. We went from a straight line from C to D to a curved line from C prime to D prime. Now here's where we start getting interesting. The lines closer to the center of curvature, here's our center of curvature at O, shorten. So C prime D prime is shorter than the line segment connecting C to D, which was delta x. So C prime D prime is less than delta x, and if we imagined a set of points down here on the bottom, which we haven't labeled, we could imagine, say we define like an EF down here on the very bottom of the beam. If we had if E prime F prime down here on the flexed beam, E prime F prime, E prime F prime, the distance of this arc would be greater than delta x. So that's an important relationship there. There's a single line somewhere in the middle where the length before and after bending hasn't changed. So as it turns out, that corresponds to the centroid, the y centroid here of our cross section. Y bar. So if your line goes through y bar and you don't have any actual normal axial stresses, then that's the y location, sort of from the top of the beam vertically to the bottom versus the direction it's flexing, where you're not going to get a length change. So that's called the neutral axis, and in this case our line that goes through AB is our neutral axis. So AB is delta x, and the length of the arc from A prime to B prime is also delta x. So that becomes very, very important in our longitudinal stress analysis. So now we're going to take this idea of the neutral axis, we're going to take the idea of the radius of curvature, which is going to vary with distance along the beam, some position, but for any given position we can make these relationships. So we're going to count on the fact that we can measure the length AB, and if it's the neutral axis, it started as delta x and it's going to end as delta x, but that delta x also can be defined as the radius of curvature times our delta theta angle, like basically, S arc length is equal to r theta, same deal. Okay, let's talk about strain. So we're going to go back to that shortened section, C prime, D prime, the one that was up on the concave section of the beam. We can go back and say, all right, well, if we can define the length A prime, B prime as rho, our radius of curvature times delta theta, we can define C prime, D prime as rho minus y. It's been C prime, D prime is at a distance y from the neutral axis. So in this case, y, remember our coordinate center is right here on the neutral axis. So C prime, D prime is at some y distance above the neutral axis, closer to the center of curvature. Okay, so we'll define the arc length. The arc length is our new kind of radius, which is rho minus y times our delta theta. Okay, if we had a before length and we had an after length, we can define an axial strain. So the axial strain, epsilon xx, at any height y above the neutral axis or at negative y below the neutral axis, just here's our definition of axial strain. So if we're going to look at it at height y, which corresponds to C prime, D prime, we can just say the arc length of C prime, D prime minus the original length CD divided by the original length CD. Just back to classic definition of axial strain. Well, the original length was just delta x, and the new length is r delta theta, where our r is rho, the radius of curvature, minus y, our y position of our line CD. So we're going to do a little mathematical magic now and see if we can't rearrange this expression into something that's super handy. So we're going to start by taking this value rho, our radius of curvature, and noticing we can redefine rho as delta x divided by delta theta. That's another definition. And so we can plop that in. Just do a little substitution. Then we can do some multiplying through. And I'll cover up my line here. And we end up with delta x minus y delta theta minus delta x over delta x. So we do some simplification, and we end up with our axial strain in the x direction at a height y above the neutral axis is negative y, the height above the neutral axis, times the change in angle that we've, over which we're looking over our flexed angle, divided by delta x, the original length. If we take the limit as delta x equals 0, we end up with this expression. So now we have d theta dx, and we can go back and back substitute because if theta is equal to delta x over delta theta, then in the limit, as things get smaller and smaller, we can also say that d theta dx is 1 over rho. So our axial strain in the x direction due to just flexing is going to be the negative of the height above the neutral axis, so height going towards the center of curvature of the flexure, divided by the radius of curvature. So as we move towards that center, we're going to contract, and as we move away from it, we're going to expand. And we're going to stop for some caveats. This assumes only elastic deformation. So far we've looked at very small angles. We've made a lot of assumptions about things like shear in the XY being negligible. These all come when we're talking about small angles, small amounts of flexion. We are nowhere near yield and plastic limits in this case. And now we're ready to make a jump where we're going to leverage that and say, okay, we're going to assume now we're nowhere near yield. So we're going to throw in Hooke's law and say we are definitely in the elastic regime. We've assumed all kinds of small angle assumptions. We're going to leverage that further and say, I want to relate strain in the x direction for any x position along the beam and any y position above the neutral axis to stress. We've got strain from the geometry. Now I want stress, because stress is something I can compare to material limits and properties. So how do I go from stress to strain? I apply Hooke's law. So I can say, all right, I know that normal stress in the x direction is 1 over the tensile modulus times, strain in the x direction is equal to 1 over tensile modulus times stress in the x direction minus Poisson's ratio times the sum of the normal stresses in the z and the y. Lucky for us, back at the beginning of the problem, we already defined sigma zz as 0 because basically there was nothing to apply stress on those lateral faces, and that we had said because there is no change in z dimension, there's no epsilon zz strain, there was no sigma z, no epsilon yy strain. The height of the beam was not, in the height dimension of the cross section wasn't changing. Tongue-tied in our orthogonal dimensions. There was no stress in that direction because we would have had a stress to change the dimension. So that's also 0. So Hooke's law gets really simple. It's just the strain, the normal strain in the x direction is the normal stress in the x direction divided by Young's modulus. Okay, so normal strain we've just determined is the distance, the negative of the distance upward from the neutral axis divided by the radius of curvature at that particular point along the length of the beam. The x dependence of this axial longitudinal stress comes via that radius of curvature, because that's changing as we go along the beam. Unless we've bent it into a circular arc, which is very rare, this rho is what's going to change as we go from one end of the beam to the other, or from one part of the beam to the other. And that's going to be a function of moment and our point loads. So all we have to do is multiply our expression for strain times Young's modulus, and now we have an expression that's relating stress, which, if y is negative, if we drop below the neutral axis, that stress is going to be a tensile stress, and it can be pretty big. Young's modulus tends to be a big number. Y can be the full height of a beam. Some beams are several feet high. So you can see that unless rho is a pretty small number, or a pretty big number, so unless we have a very small curvature, our sigma xx can be getting up into some pretty big numbers. So now we're going to do a little relationship to other definitions for stress, and we're going to define a little bit more usable formula, because rho is still a little bit difficult to define. I mean, technically maybe you could go out and measure it, but there's better ways to express that, and we might want to express it in terms of something that we can solve for, like moment, that we can just solve for with statics without having to get out and do some, real crazy, some measurements on a loaded beam. So what we want to do is we want to relate our stress in the x direction, our normal stress in the x direction, to moment. If you remember back at the beginning of Beam's lecture 1, we had a relationship that said for a 2D beam, the moment at any point due to stresses in the sigma xx stresses were going to be the integral of those stresses integrated over the entire area of the end of the beam times the y position of that little bit of area that we cared about. Oh, well, now we're in a situation where sigma xx is dependent itself on its y position, linearly. In fact, the further we get from the neutral axis, the bigger sigma xx is. So we can drop this expression for sigma xx in here into our integral, which is related to moment. So now instead of integrating y, just some unknown expression for sigma xx, now we have a known expression. We're going to integrate y times negative y times the tensile modulus divided by the radius of curvature. Unless the beam is not homogeneous, not isotropic, non-uniform, which is rare, these two are not going to be dependent on area. The modulus is going to be uniform over the whole area, and unless the beam has got a kink or something, the curvature is going to be the same. So we can pull these two out of the integral, and those stay up front, and we're left with the integral of y squared dA. Now, for anyone who is remembering dynamics, you might remember that this is something familiar. This ends up being a moment of inertia. So we'll in the y, the IZZ, so we'll revisit that. But first, let's resubstitute, because we've still got, tensile modulus is easy to look up, but we've still got this expression for rho at the bottom. So we're going to do a bit of a double substitute. So we get rid of this expression for rho, which is, again, something you'd have to measure. So we're going to go back and resubstitute and say basically go back to this formula and say, if we divided both sides by negative y, we could say sigma xx divided by negative y is equal to tensile modulus over rho. Okay, so we can put this right there in front of the integral. So now we can relate moment, which is something we can calculate with statics, to stress, which is something that we might want to compare to like a maximum limit in a handbook like yield stress or something, divided by the distance from the neutral axis to any position we care about, times this integral of y squared dA. And we can rearrange it again if we want to isolate stress, like assuming we can solve for the moment at any position, like maybe the maximum position, using maybe a shear and bending diagram. So we can say that our longitudinal stress, or our sigma xx, normal stress in the x direction, is going to be negative the internal bending moment at that x position times the y distance upward from the neutral axis. So if we're moving towards the center of curvature, it's positive. If we're moving away, it's negative, divided by this integral of y squared dA, which ends up being the moment of inertia of the cross section about the z-axis at the centroid. So I'm gonna try to freehand a beam here for you. So imagine we've got a cross section of a beam, and here's the centroid. We've defined y going in this direction. X is going out along the beam if the beam continued to the edge of the paper. Here's z. And z is the z-axis is going straight through the centroid. So when we look at IZZ, we're basically looking at how easy it is to rotate about the z-axis, which is why we care about the y position. So we're back to the definition of centroid. So this is IZZ. And if you remember work from your dynamics class, perhaps, where that was used for some rotational calculations, this is entirely dependent on geometry. So we can basically calculate that integral for any geometry. There's no mass dependence at this point. This is all about geometry and stiffness. So we don't have a density function. So rho here was radius of curvature, not density. So in a lot of cases, we can just look up our IZZ for some classic shapes, squares, circles, rectangles, and then use things like the parallel axis formula and an addition of integrated areas to add and subtract what we need for different beam shapes. But we know that's something that we can calculate as long as we know the dimensions of the cross section. So here we go. The stress, normal stress in the x direction, so longitudinal stress in the beam, at any point x along the beam, at any distance y above the neutral axis of the beam, is going to be equal to negative the distance from the neutral axis, above the neutral axis, times the applied moment at that position. So that's the internal moment that you would solve for on a shear and bending moment diagram, divided by the moment of inertia in the z direction through the centroid of the cross section. You can look that up or calculate it easily for any cross section. Why? It's going to depend. So if you think about what this would be at the neutral axis, y would be 0. There's no longitudinal stress other than maybe what you have from axial loading, which we're not considering here. If moment is 0, if we're not applying any moment, or that moment happens to be 0 at that particular point, then also there's no longitudinal stress, no worries. But where we'd want to worry is if we're looking at a point down here on the bottom, at a point along the beam, and I'm going to go back to material from a previous lecture, where maybe the internal moment m as a function of x is a maximum, and maybe we've picked a beam with a very small moment of inertia, a small IZZ. This might get pretty big. Furthermore, this negative sign says as we travel from the neutral axis towards the center of curvature and we're contracting, we have compressive stresses. No worries for most materials. But if we travel away from the radius of curvature on the concave or the convex axis or convex side, aka this side, we're stretching. So as we drop below the neutral axis, going away from that center of curvature, we have tensile stress. So if you were to say, okay, I want to design a beam around the worst possible case, right? I've got to pick a material, or I've got to pick a cross-sectional shape that's big enough. I'm stuck with the material. I know what my maximum longitudinal stress is. I'm going to base it on some safety factor versus my yield stress, say. Something that I don't want to cross. I know that my y maximum, all other things being equal, is going to be the furthest distance I can get from the neutral axis. So as soon as I've picked a cross section, assuming I know where the centroid is, I go to the farthest point from that centroid in the direction away from my center of curvature, like away from the direction I'm bending it in, and that defines my maximum tensile stress, assuming that I know the maximum moment at any point along the beam, which I could do with my static shear and bending. So I can define my worst case. So I can either define, okay, how big of a yield stress of a material do I need? Or how big of a moment of inertia do I need to design in? Or do I need to limit the applied bending moment? So I have 3 knobs that I can turn to make sure that I stay within a safe longitudinal stress. I limit that tensile stress to something that is tolerable for the material, and that allows me to use a cross section that maybe saves weight, that gives me, basically whatever I need to fit into my design. The internal moment at that point is in many cases going to be a function of your loading, but if you maybe have an existing design and you are re-rating it, how big of a truck can I drive over this? How much can we put on this? How much weight can it carry? You would use the other factors and put a safety factor on your sigma xx and say, yea, verily, this can only be so big. So this is known as the flexure formula. because it is looking at stresses that are due exclusively to flexion. We'll look in a follow-on lecture at the effect of a true axial stretch or compression on this sigma xx. It'll add to it or subtract from it, and it'll also actually move the position of the neutral axis. But a general rule of thumb is down at this farthest distance from the neutral axis for most bending scenarios, the tensile stress due to flexure tends to be much bigger than the types of the stresses that are practical to apply with an axial load. So if you really want to apply a lot of tensile stress to something, just support it between 2 points and step on it in the middle. It's much easier to get a huge tensile stress down on that bottom curved surface than it is to actually grab something and yank on it. So we'll have an example later on where we'll take a look at relative magnitudes. In real practice, you should consider both. But the flexure formula takes into account what is typically the largest one. So that is it for this lecture. We will pick up a little bit more application of the flexure formula in our next lecture.